In this lesson, we're going to talk about something called glycolysis. So what is glycolysis? Well, if we break down the word glyco plus lysis, what does the word lysis mean? Lysis means to split apart, and glyco is associated with the word sugar. So glycolysis, you're splitting apart a glucose molecule. Glucose is a 6-carbon molecule. And in glycolysis, glucose will be split apart into 2 molecules of pyruvate. And each molecule of pyruvate represents a 3-carbon molecule. And so basically, you're taking glucose and breaking it apart in half, so to speak. And that's the basic idea behind glycolysis. And in this process, some of the energy that's released as glucose converts into 2 molecules of pyruvate is captured in the form of ATP and NADH. So glycolysis is an energy producing process. Now let's discuss the net reaction of glycolysis. So glycolysis takes place in the cytosol of the cell. And in the net reaction, we're going to start with a molecule of glucose, which will react with 2 NAD plus molecules and 2 ADP units, or adenosine diphosphate, with 2 inorganic phosphate ions. And this is going to produce 2 molecules of pyruvate plus 2 molecules of NADH. Going from NAD plus to NADH, is that a reduction process or is that an oxidation process? What would you say? Anytime you add hydrogen to a molecule, you're reducing the molecule, so that is a reduction process. Now, in addition to forming the 2 NADH molecules, 2 hydrogen ions will form and 2 units of ATP will be produced. So we're converting ADP to ATP by the addition of a phosphate unit. And then we'll also get 2 water molecules. So that's the net reaction of glycolysis. Now, glycolysis can be broken up into 2 phases, and it occurs in 10 steps. So in the first phase, which represents steps 1 to 5, this is known as the investment phase. And the second phase, which occurs through steps 6 to 10, is known as the payoff phase. Now, when you hear the word investment, what comes to your mind? What do you think about? When I hear the word investment, I think of the stock market. Maybe you want to invest $1,000 in stock so you can sell it for a higher price, maybe $2,000. And so when you think of the word investment, it carries the idea that you have to buy first in order that you can sell for more later. In the case of glycolysis, you need to put in energy so that you can get more out later. And in the first phase, it's endothermic, so to speak. It consumes energy. And in the second phase, it's going to produce energy, but more energy than what you put in. In the first phase, you need to put in 2 molecules of ATP to get the process going. But in the second phase, you're going to get 4 molecules of ATP. In addition, you're also going to get 2 molecules of NADH. So that gives us a net gain of 2 molecules of ATP and 2 molecules of NADH. So now let's go over the 10 steps of glycolysis. So here we have step 1 of glycolysis, and on the left we're going to begin with a molecule of glucose. That doesn't look like a U, so let's fix that. Now, what's happening in this reaction? What is the difference between the structure on the left and the structure on the right? Notice that a hydroxyl group is replaced with a phosphate group. Now, what do you think is the name of the product of the first step of glycolysis? What is the name of this molecule? Well, let's find out. This is carbon 1, 2, 3, 4, 5, 6. So we have a phosphate group attached to carbon 6. And the substrate is a glucose molecule, so this is going to be called glucose 6-phosphate. Now, what is this process called? The process of adding a phosphate group to a molecule. This process is known as phosphorylation. We're phosphorylating glucose to create G6P, glucose 6-phosphate. Now, where does the phosphate come from? The phosphate comes from a molecule of ATP, which is converted to a molecule of ADP. ATP is known as adenosine triphosphate, and ADP is adenosine diphosphate. So ATP has 3 phosphate units attached to it, and ADP has 2 phosphate units attached to it. So going from ATP to ADP, it gives up a phosphate group, and there is an enzyme that helps us to transfer that phosphate group from the ATP molecule to the glucose acceptor molecule, giving us glucose 6-phosphate. Now, what is the name of that enzyme? That enzyme is called hexokinase. So a kinase enzyme catalyzes the transfer of a phosphate group from ATP to another acceptor molecule. And the word hexo is due to the fact that the acceptor molecule, glucose, contains 6 carbons. Hexo means 6. Now, there's something else that's needed in order for this process to work. And it's a cofactor. It's the magnesium 2+ ion. So you need this ion in order for this reaction to work. Now, is this a reversible reaction or an irreversible reaction? Can the reaction only go to the right, or can it go in both directions? Now, under intracellular conditions, the standard free energy change for this reaction, at least according to my textbook, some numbers can change over time, it's negative 16.7 kilojoules per mole. And I am running out of space here, so if you see me writing very small, it's because there's not much space left. But that's the standard free energy change for this reaction. And because it's relatively large for intracellular conditions, this reaction is irreversible. So if you see a single arrow, that means it can only go in one direction. It's irreversible. If you see a double arrow, that means that it's reversible, and the standard free energy change will be lower if you ignore the negative sign. So if you have a very large negative delta G value, it's going to be irreversible. However, if it's very small, it will be reversible. Now, one thing I do want to mention before moving on to step 2 is I think I wrote delta G naught is equal to negative 16.7 kilojoules per mole for the first step of glycolysis. But this should be delta G prime naught. Now, if you compare it to delta G, which is negative 34 kilojoules per mole, the reason why it's different is due to the pH values. Delta G prime naught is based on a pH of 7 because most cells, they exist in an environment with a pH of 7, where the H plus concentration is 1 times 10 to the minus 7. And so this represents the biochemical standard free energy change. Now, the one that chemists and people who deal with physics, they tend to use this. For this one, the pH is 0 and the H plus concentration is 1 molar or 1 mole per liter. And so from a biochemical perspective, this is not very useful because most cells, they don't exist at a pH of 0. They exist at a pH of 7. So the delta G values that I'm going to write in the future will be the biochemical delta G standard values. Now let's move on to step 2 of glycolysis. So on the left, we have G6P, glucose 6-phosphate. And what is the name of the molecule on the right side? So take a minute, pause the video, see if you can come up with the name of the molecule. So notice the location of the phosphate group. It's still on carbon 6. Now we don't have a glucose base unit, but looking at this, what type of sugar do you think this is? Glucose has a 6-membered ring, but fructose has a 5-membered ring. So the name of this particular molecule is called fructose 6-phosphate because we still have the phosphate group on carbon 6. Now the delta G value for this particular reaction, the biochemical delta G value, it's positive 1.7 kilojoules per mole. So based on that value, would you say that this particular reaction is reversible or irreversible? Now, if we look at the magnitude of this number, it's about 10 times less than the value that was in step 1, which was 16.7. So because this is so much more smaller, we're going to say that this reaction is reversible. Now this reaction is facilitated with the magnesium 2+ cofactor, so we need that as well. Now looking at the reactant and the product for this step, what is the relationship between the two? What is the relationship between glucose 6-phosphate and fructose 6-phosphate? Well, the phosphates group, they haven't changed, so they're still the same. The only difference is going from glucose to fructose. And glucose and fructose, they're basically isomers of each other. So with that in mind, what type of enzyme do we need if we want to create an isomer, if we want to catalyze a rearrangement reaction? What type of enzyme will help us to do that? So for rearrangement reactions, you need an isomerase. I think I said that wrong. Isomerase enzyme. Specifically, you need a phosphohexose isomerase enzyme. Now, why the word phosphohexose? Well, this word is associated with the reactant. If you look at the reactant, it's a hexose, it has 6 carbons, and it has a phosphate group. So thus it makes sense that this is a phosphohexose isomerase. And it also works for the right side as well because it can go this way. The product is also a hexose. Fructose is a 6-carbon sugar, and it has a phosphate group attached to it. Now let's move on to step 3 of glycolysis. So on the left side, we have fructose 6-phosphate. And what is the product on the right side? What is the name of that molecule? So this is carbon 1, 2, 3, 4, 5, 6. Do you notice any differences between the reactant and the product? So notice that a hydroxyl group was replaced with a phosphate group. So in the product, we have 2 phosphate groups. We have one on carbon 1 and on carbon 6. So therefore, this is going to be called fructose 1,6-biphosphate. So I'm going to write BP for biphosphate. Now, if you recall from step 1, what is the name of the process where we're adding a phosphate group to a molecule? What is that process called? So that process is known as phosphorylation. This process, step 3, is known as the phosphorylation of fructose 6-phosphate into fructose 1,6-biphosphate. Now, where does the phosphate come from? So based on step 1, it's going to come from an ATP molecule. And so when ATP loses a phosphate group, it transforms into ADP. Now, like step 1, we're going to need a magnesium 2+ ion to facilitate this reaction. Now, what about the enzyme for this reaction? What type of enzyme do we need? What type of enzyme catalyzes the transfer of a phosphate group onto a fructose substrate? Based on step 1, we know that a kinase enzyme will catalyze the transfer of a phosphate group to a molecule. Now, looking at the acceptor molecule, it's fructose and it has a phosphate group on it. So this particular enzyme is appropriately called phosphofructokinase. In short, it's also called the PFK1 enzyme. So that's the abbreviation for it. And it should be a 1 here too. It's phosphofructokinase 1. Now let's talk about the reversibility of this reaction. The standard free energy change for this reaction, the biochemical version, is negative 14.2 kilojoules per mole. So based on this value, would you say that this reaction is reversible or irreversible? Now, this value is pretty close to the value in step 1, which was negative 16.7. So this particular reaction is not reversible. Under intracellular conditions, it proceeds in the forward direction. Now let's move on to step 4 of glycolysis, the cleavage of fructose 1,6-biphosphate. So notice that we get 2 molecules, a ketone and an aldehyde. So what do you think are the names for these molecules? A 3-carbon aldehyde with hydroxyl groups is known as glyceraldehyde. And if you count the carbons, the aldehyde has the highest priority, so that's carbon 1. You'll find that the phosphate group is located on carbon 3. So this is called glyceraldehyde 3-phosphate. And this one is called dihydroxyacetone phosphate. A 3-carbon ketone is known as acetone. Now, is this reaction reversible? The delta G value for this reaction is positive 23.8 kilojoules per mole. Now, this is a high number and it's positive, so that indicates that it favors the reactant on the left side. Now, keep in mind, this is the biochemical delta G value and not the other one that's based on chemistry and physics. It turns out that this particular reaction is reversible. Now, we're going to talk more about that later, but the enzyme that catalyzes this reaction is known as the aldolase enzyme, which is used to catalyze a reversible aldol condensation reaction, which is what we have in step 4. Now, let's talk about the reversibility of the reactions in glycolysis. Now, for those of you who just want to know which steps are irreversible, for those of you who prefer memorization, steps 1, 3, and 10 are irreversible. The rest are reversible. So if you know that, you don't have to go any further. Now, for those of you who want to understand it, let's take the chemist's view of delta G. So this is delta G naught. Notice that when you have a very high negative value, the reaction is irreversible. It's product favored. And if you look at the other values, they're very small. They could be positive or negative, and those are the reversible reactions when delta G is close to zero. Now let's say if you're given the biochemical delta G value and you want to use that to determine if it's reversible or not. Notice that all the ones with a positive value are reversible. There's 4 that have a negative value, and 3 of these are irreversible. So this is the only exception you have to watch out for. But if you're given the biochemical delta G value, then if you get a positive delta G for glycolysis, it's going to be reversible. Now let's move on to step 5 of glycolysis. So this is the last step of the investment phase. In this step, we're going to convert dihydroxyacetone phosphate, which I'm going to call DAP, into glyceraldehyde 3-phosphate. Now this is a reversible reaction, and looking at the reactant and the product, what's the chemical relationship between them? Notice that they both have 3 carbons, 5 hydrogen atoms, 6 oxygen atoms, and a phosphorus atom. So because they have the same number of atoms but a different structure, these 2 species are known as isomers. So this is a rearrangement reaction. And what type of enzyme catalyzes a rearrangement reaction? If you recall, it's an isomerase enzyme. Now let's focus on the substrate molecule that we have here. So we have a 3-carbon keto sugar, or just keto sugar, with a phosphate group attached to it. So the enzyme that we need to catalyze this reaction is going to be called triose, because we have a 3-carbon sugar, triose phosphate isomerase. Now, it's important to understand that as we get into step 6 of glycolysis, the beginning of the payoff phase, 2 molecules of G3P enter that phase. So if you need to calculate the number of ATP molecules and NADH molecules in that phase that's produced, you need to double everything. So let me give you an overview. So in step 4, we produced 2 different molecules, dihydroxyacetone phosphate and G3P. Now in step 5, this molecule, dihydroxyacetone phosphate, gets converted to G3P. So if we start from our original glucose molecule, at the end of step 5, we have 2 G3P molecules. So going from step 6 to step 10, we need to double everything since we have 2 of these molecules. Keep that in mind. Now let's move on to step 6 of glycolysis, the beginning of the payoff phase. So on the left, we have G3P, glyceraldehyde 3-phosphate. And what do you think we have on the right side? So we still have a 3-carbon molecule, but it's not going to be called glyceraldehyde because we don't have an aldehyde functional group. So this is an aldehyde functional group. As you can see, we have a phosphate now. Now, instead of the hydrogen, we do have an oxygen. And so this is an aldehyde, and this is a carboxylate group. So instead of glyceraldehyde, we now have the name glycerate. Now we also have 2 phosphate groups attached to this molecule. We have a phosphate on carbon 1 and on carbon 3. So to put that all together, it's going to be called 1,3-biphosphoglycerate due to the carboxylate group that we have at the end. And bi means 2. So that's the name for the product. Now what else do we know about this reaction? The conversion of G3P to 1,3-biphosphoglycerate, is that an oxidation reaction or is that a reduction reaction? Now to give you a hint, in this reaction we have the conversion of NAD plus into NADH. And it also produces an H plus ion. Now the conversion of NAD plus to NADH, is that an oxidation or reduction reaction? Now keep in mind, for every oxidation reaction, there is a corresponding reduction reaction. And just to review, oxidation occurs when you either remove hydrogen or if you add oxygen. Reduction occurs if you add hydrogen or if you remove oxygen. So looking at this reaction here, going from NAD plus to NADH, we're adding hydrogen. So that is a reduction reaction, which means that the conversion of G3P to 1,3-biphosphoglycerate must be an oxidation reaction because that's the other reaction. And you could see it. Here, we're removing hydrogen, so that's oxidation, and we're adding oxygen, which is also oxidation. So G3P is oxidized to 1,3-biphosphoglycerate, and at the same time NAD plus is reduced. Now it's important to understand that this hydrogen here ends up in the NADH molecule. Now the hydrogen that's part of phosphoric acid, well that's not really phosphoric acid, but that's it's an inorganic phosphate. Phosphoric acid will have 3 hydrogens. So that's hydrogen phosphate, if you want to call it that. But this hydrogen ends up here. That's an acidic hydrogen with a +1 oxidation state. Now let's talk about the enzyme that catalyzes this reversible reaction. What type of enzyme do we need? So I'm going to give you the name this time. It's glyceraldehyde 3-phosphate. So this is the name of the substrate. That's G3P. And then dehydrogenase. Now let's focus on the word dehydrogenase. What does that tell us? So the suffix ase tells us that it's an enzyme. Dehydro, that is the removal of hydrogen. And so the dehydrogenase enzyme facilitates the removal of hydrogen in an oxidation reaction in order to reduce NAD plus into NADH. So anytime you see this enzyme, know that it oxidizes a substrate by removing hydrogen, and at the same time it can reduce NAD plus to NADH. Now the last thing I want to talk about in this particular step are the numbers. So as we said before, there's 2 molecules of G3P that enters step 6 of the payoff phase. So that means that 2 NAD plus really gets reduced to 2 NADH. And in the bottom, I wrote down the net reaction. So here you can see the 2 NAD plus that reacts with glucose, even though not directly, and the 2 NADH that we get. Now, even the H plus, we need to multiply that by 2. So in the end, we get 2 H plus as well. Now, there's one more piece to the puzzle, and that's the inorganic phosphate. So if we multiply it by 2, we can see that it shows up here in the overall net reaction. So it's good to keep in mind or keep track of what's happening in each reaction. what's being oxidized, what's being reduced, and things like that. So now you know where, not that one, but where these reactants and products show up in the individual steps in glycolysis. So they show up in step 6. Now let's move on to step 7 of glycolysis. So let's begin by figuring out what the name of the product is. Now for the reactant, we know that it's 1,3-biphosphoglycerate. Based on that, can you predict what the name of the product will be? So notice what's different. We lost a phosphate group. So we're still dealing with glycerate, but we don't have a phosphate group on carbon 1. We only have it in carbon 3. So instead of saying 1,3-biphosphoglycerate, this is simply 3-phosphoglycerate. So that's the name of the product for this reaction. Now, where did the phosphate group go? What happened to it? The phosphate group was transferred to a molecule of ADP to produce ATP. And this process is known as substrate level phosphorylation. It's the formation of ATP by a phosphoryl group transfer. Now, what about the enzyme for this reaction? What type of enzyme is used to transfer phosphate groups? So that enzyme is known as a kinase enzyme, but particularly this one is going to be called a phosphoglycerate kinase enzyme. And it makes sense because we're dealing with a phosphoglycerate molecule, in this case biphosphoglycerate. Now something I want to focus on is the production of ATP. Now remember, we're still in the payoff phase, so everything has to be multiplied by 2. So here we're consuming 2 ADP to make 2 ATP. In the investment phase, we had to put in 2 ATP units. In the payoff phase, we're going to get 4 with a net gain of 2. But right now, this 2 units of ATP represents a portion of the 4 that we need to get during the payoff phase. So it doesn't represent the net gain. It's simply half of this number. The last thing I want to mention about this reaction is that it does require a magnesium 2+ ion to work as well. And so that concludes step 7 of glycolysis. Now let's talk about step 8 of glycolysis. So on the left, we have 3-phosphoglycerate. So based on that, what is the name of the product on the right side? Feel free to pause the video and work on it. So if you look at the product and compare it to the reactant, notice that in this reaction, the phosphate group has been shifted from position 3 to position 2. So therefore, to name this product, it's 2-phosphoglycerate as opposed to 3-phosphoglycerate. Now, what type of enzyme moves a functional group from one position to another? Now, granted, these are isomers. So if you were to say an isomerase enzyme, you're not technically incorrect because the enzyme that I'm looking for is a type of isomerase enzyme. It has a specific name. So this particular enzyme is a mutase enzyme. It's a type of isomerase enzyme, but specifically, its purpose is to move a functional group from one position to another. In this case, to move the phosphate group from position 3 to position 2. So how can we name the complete enzyme that we need for this reaction? So all we need to do is look at the substrate molecule before, phosphoglycerate. So this particular enzyme is called phosphoglycerate mutase. It catalyzes a reversible reaction using the magnesium 2 plus ion cofactor. And so that's basically it for step 8 of glycolysis. Now, I know some of you might be excited that we're getting close to the end. It's been a long video, full of information. But before I continue, I just want to recommend that you subscribe to this channel, particularly if you like this video. It's a good way to show appreciation for it. And don't forget to click on that notification bell. I do have other videos on other topics like chemistry, physics, algebra, trig, pre-cal, calculus. So if you need help in those subjects, feel free to check out my channel and you can find playlists on those topics. But now let's continue on with step 9. Now the first thing I'm going to ask you is, what type of reaction do we have here? Is it a rearrangement reaction, a condensation reaction, a substitution reaction, or something else? So notice what's happening. We're losing a hydrogen and a hydroxyl group. So therefore, water is a side product of this reaction. So this is a dehydration reaction. We're removing water out of the equation. Now, we said that the name of this reactant, which is the product of the last step, is 2-phosphoglycerate. What do you think the name of the product will be? Now, this one might be a little hard to figure out, so I'm going to give it to you. The product is called phosphoenol pyruvate. Now, if you don't know the structure of pyruvate, it might be a little bit more difficult to figure that one out. Pyruvate has a carboxylate group, and attached to this carbon you have a ketone, and you do have this group as well in pyruvate, but it's going to be a CH3 instead of a CH2. Now we can see why we have the word phospho there, because we have a phosphate group attached to it. But what about the word enol? An enol is basically an alcohol attached to an alkene. Think of ene from alkene and ol from alcohol. So this here is an enol. And you could kind of see that here. I mean, we do have the alkene from the C double bond C, and you do have a CO bond. So thus you have a phosphoenol group because of the phosphorus here. Now, what type of enzyme will catalyze this reaction? Now, this might be hard to figure out, so I'm going to also give this one to you. It's an enolase enzyme. The reason for this is that this reaction proceeds through an enolic intermediate, and so this enzyme helps to facilitate that process. And that's basically it for step 9. So we have the dehydration of 2-phosphoglycerate into phosphoenol pyruvate. And so we get 2 water molecules because there's 2 G3P molecules starting with step 6. So in the net reaction, which I had before, there's 2 H2O molecules, and this is the reason why. Now this is the last step of glycolysis. So if we backtrack to the previous step, we said that 2 water molecules were formed, and so we could see that in a net reaction. Now in step 10, phosphoenol pyruvate is going to convert into pyruvate. And the cofactors that are needed for this reaction are the magnesium and the potassium ions. So what type of enzyme do we need? Notice that we're losing a phosphate group. So anytime you're dealing with a transfer of phosphate groups, you need the kinase enzyme. This one is going to be called pyruvate kinase. Now, what happened to the phosphate group? Where did it go? Based on the previous examples, we know that it was transferred to a molecule of ADP to produce ATP. Now, for every step in the payoff phase, we need to multiply it by 2 because we know we're going to get 2 pyruvate molecules at the end. So we need to use up 2 ADP molecules to make 2 ATP molecules. In the investment phase, we had to use up 2 ATP molecules. In the payoff phase, we gain 4 ATP molecules. So this is the other half of the 4 ATP molecules that we've generated in the payoff phase. So if you want to find out where we got these 2 ATP molecules, or rather where we consumed them in the investment phase, this is found in steps 1 and 3. Now, these 4 ATP molecules, they're found in step 7 and 10. So remember, you need to double it. So in step 7, we generated 2 ATP molecules, and in step 10, we generated another 2 ATP molecules. In steps 1, we used up an ATP molecule, and in step 3, we used up another one. And so we had a loss of 2 ATP molecules, a gain of 4, so we have a net gain of 2 ATP molecules in glycolysis. And that's basically it for this video. I know it's been a very long, very detailed video, and some of you out there might only needed a basic overview of glycolysis. But I know there's some of you who wanted a more detailed video. And I didn't see a very detailed video in YouTube. There might be some out there, but I didn't see it, so I decided to make one. Hopefully you found it to be helpful, and if you did, feel free to subscribe, and thanks again for watching.